let's start with the first one. Okay, this is example 2.8 of our textbook. So let's see that. So it says a slab of material of dielectric constant K. So we have a slab, and this slab has got a dielectric constant, and this dielectric constant is K. Okay, has the same area as the plates of a parallel plate capacitor. So we have a capacitor, and the type is a parallel plate. Parallel plate, and this plate area and the area of this slab both are same plate area as that of the slab. Okay, but has a thickness. So it has a thickness which is 3/4D. So the slab has got a thickness, and the thickness is 3/4D, where D is the separation between plates. Right? This is the separation between plates. How is the capacitance changed when the slab is inserted between the plates? So we have to find out what is the capacitance when the slab is inserted between the plates. So this is a known phenomenon that whenever you enter a plate, a dielectric, the capacitance is always going to increase. It will be K times the capacitance when the capacitor was only a parallel plate capacitor with what? With the with air in between it. Okay, so let's clone this, and this is the original capacitor, right? And D is now we also have something which is known as the dielectric. We also have a dielectric, and the dielectric, I can't do anything with this one. The dielectric has the same. The dielectric has the same area as that of the parallel plate, but the dielectric has got a thickness, and the thickness is such that it is 3/4 of D. 3/4 of D. Do you understand what is 3/4 of D? 3/4 means 1/4 portion is still blank. So you can either put that dielectric on one side or in between, whatever it is. Have you understood? So first we will calculate what is the capacitance of this capacitor. Means let's first find out what is C0. So C0's value should be how much? Epsilon 0 A upon D. Right? The areas are same. Now, when the condition is C0, the book is saying that the electric field is E0 between the plates. It's E0. After you enter the dielectric, the electric field will get reduced. The electric field gets reduced, and once the dielectric is inserted, your electric field will be E, which will be E0 upon K. Everything is K. So if you divide it by K, the value will be coming down now, right? This is E0 by K. And similarly, the potential difference. So what is your potential difference? Your potential difference is always E multiplied by D. This is standard value. Now, what is the potential difference between the two plates? Please understand, a capacitance increases or decreases based upon how much of dielectric you have inserted. But you increase that capacitance by once a dielectric is inserted, for a less increase in voltage, more capacitance can be done there. Have you understood? So V is equal to ED. Now, how will, in your case, how is the V applicable? You will use this E for the amount of thickness for which the dielectric is responsible, and you will use this E for the amount of thickness for which the gap is applicable. So 3/4 of this difference you have actually filled up with E0. Sorry, with E, right? So this V should be, if I do like this, 3/4 of E multiplied with, better it makes a sense if I write it like this, E multiplied by a 3/4 of D, right? And it should be an E0 multiplied for 1/4 of D. Have you understood this? Right? So let's do that. 3/4 and 1/4. Now, how do you solve this? So we will write our V is equal to E0 into D by 4, and instead of E we can write E0 by K. E0 by K 3/4 of D. Okay? So ultimately E0D can be taken out as common. This is D by 4 plus 3. Oh, sorry. This will be 1/4 plus 3/4 K. 1/4 plus 3/4 K. So if you do it further, it will be ED. So 4K and 4K. So 4K will be our LCM. 4K divided by 4 is 4. So here we will get K plus 3. Fine. So V. Okay. ED means V and E0. Oh, this is E0, sorry. Yeah. So we can write our V is equal to V0 times K plus 3 divided by 4K. K plus 3 divided by 4K. So potential difference decreases by this particular value. This value will be less than, this value will be less than 1. So potential, because K is always greater than 1. So this value will be less than 1. K is greater than 1. So if you will take 2, so this is 2 plus 3, 5, and 4 plus 2, 4 into 2 will become 8. Is this understood? So you can write that the potential, can I just write it here? The potential reduces by a factor K plus 3 by 4K. Means the new potential will be V0 times K plus 3 by 4K. The potential reduces. So if the potential reduces, the capacitance increases. There won't be any difference in charge. So our capacitance is, initial content of charge was Q0. Now your voltage has become V. So you, in place of V, you can enter. So C becomes Q0. For V, we will write V0 into 4K by K plus 3. Did you understand this? Now this value is greater than 1. So this is your new capacitance is previous capacitance multiplied by 4K by K plus 3. Means the capacitance increases by a factor 4K by K plus 3. We'll revisit, don't worry. Capacitance increases by a factor 4K by K plus 3. So what was the problem all about? The problem was that we had a parallel plate capacitor where a dielectric slab of thickness, which of certain thickness, which is equal to how much? 3/4 of the space in between it is being inserted. Area of the dielectric slab is same as that of the area of the capacitor plate. So they're asking, what is the change that you expect in the capacitor? What is the change that you expect in the capacitance of the capacitor? So we say that, let's say the amount of charge that the capacitor is holding is Q naught. Please understand, a capacitor's capacitance increases or decreases based on not this, based on this. Because every time you enter a dielectric, how does it affect on this one? Because these plates are connected to a battery, they will get charged. But the capacitance is charge divided by voltage. So your eyes should always be on the voltage. If this is lowered or increased, automatically the capacitance will change. And we know that if you have a parallel plate capacitor, the capacitance is, say, C0. C0 is what? Epsilon 0 A by D. And if you have a parallel plate capacitor replaced by a dielectric with dielectric constant as K, then the new capacitance is K times. So for this dielectric, this was a very strange dielectric which was not completely filled. So we could not use K. For it, the applicable value of K is this big, 4K by K plus 3. Are you understanding? Had this dielectric completely filled this space, then so much of calculation was not required. In that case, the new capacitance will be C0 times of K. But the dielectric is not completely filling. There is some portion of air and rest of the portion by the dielectric. So we need to see what is the impact on the voltage. So we say that if you have an electric field, so what did we say? Let the original electric field be around E naught. Let the original electric field be around E naught, means when you have air in between it. And E naught and E are always related by E equal to E naught by K. Understood? So we now try to find out what is the impact of voltage. Voltage is always electric field into D. Now the electric field E naught is applicable for air portion, E is applicable for dielectric portion. So what did we do? We have taken E naught into the air portion and E into the dielectric portion. Then we substituted for E in terms of E naught. And finally we found out that our voltage is coming as E naught D. Now what is E naught D? E naught D is the voltage for the parallel plate capacitor, which is V naught. So we are saying that this is nothing but V naught into this. K's value beta is always more than 1. Take any value. Let's say more than 1 means even if you take 2, 3 plus 2 is 5, 4 into 2 is 8. So this factor is less than 1. That means your voltage has now reduced, and voltage reduces, we know that. So if the voltage has reduced, the capacitance should go up. So we say that the capacitance is always the charge divided by the voltage. This is capacitance with all this disturbance that you have done. So capacitance divided by the voltage developed by your disturbance. This voltage is what? V naught into K. So this has gone up. Now it is 8 divided by 5. So the factor is more than 1. And this is actually K. Is this clear? Okay, one more thing I'll just tell you. It's like this. See, don't get confused. You have a parallel plate capacitor. Okay. This capacitor can have air inside it, or it can have a dielectric. Have you understood? This dielectric can fully fill D or partially fill D. In either case, the capacitance will go up. Let's see what happens in the case of air. Then we say this is a very unique capacitance, which is epsilon 0 A by D. I'm writing it as C0. If it is fully filled with a dielectric constant, which is K, then it is how much? C is equal to K times of C0. Our question was here where it was filled for only 3/4 of D. Here we found out that the capacitance is 4K by K plus 3 times of C0. Because you were filled only up to 3/4, right? In this case, my voltage V naught is for air, will always be the electric field E naught multiplied by D. Understood? In this case, my voltage V will always be E multiplied by D, where E is less than E naught. And E naught is always, E is always E naught divided by K. Is this clear? K is greater than 1. In this case, there is a combo deal. We will have a voltage. The voltage V will be, we will say it will be E naught applicable for 1/4 of D and E applicable for, and then you just substitute this. This is what, this is E naught upon K and then you take out E naught and D outside. So this is basically your V naught and you have these two. Now I think you know how to do.
Question is like tracking sections of dielectric.
Which question?
I don't understand.
Put it up then. Okay. Triangular section means, again, you have to see how much portion is with air. Two dielectrics, yeah, combination of two dielectrics, then it will be air portion, or it can be something like this. See, say my dielectric slab is in this manner, the whole dielectric, agreed, and it is like this. This portion is with K, this portion is with K1, and this is K2. So we will take the voltage now as what? The voltage will be for K1, it is say E1. Distance is completely filled. The distance is completely filled. But K1 is applicable for half of the area. K2 is applicable for half of the area. That is the logic it goes. Is this understood now? Okay. So you have to do for V. Okay, let's take there's another problem now with combinations. These are most of the weird problems will be there as examples. Let's see our combination. Could you copy this? This is a holistic idea how the things happen. If you want, you can copy this down. This will give you a holistic idea about how the capacitance works. Insert a dielectric, the electric field goes down, the V goes down, the C goes up. Remember that. Partially filled can be in a different way also. See, Zoe, in your case, it was partially filled, means that in your case it is fully filled, but half with K1, half with K2. So apply the logic, horses for courses. Okay? Arjun, clear na? Start doing your 2-marker questions, beta. 1 mark, 2 marks, just keep on doing. Practice as much as the more you do, first time you won't be able to solve all. And even in your tests, which will come up, that will come in that pattern only. 1 mark means 1 mark, 2 marks, the way it comes in main exam. So it will be coming up in that manner. Chale aage? Right? So our next question is, we have a network of 4 capacitors. So we have 4 capacitors, and this is also pretty easy. 4 capacitors, 10 microfarad each. 10 microfarad each. And they are connected to a 500 volt supply, and the connection is somewhat like this. Okay, they are connected to a 500 volt supply, and our connection is something of this type. Fine. So this is capacitor 1. It needs to be a little bit less in its width. Pardon my width. There are 4 capacitors, and the capacitors have been named as C1, C2, C3, C4. So this is C1, C2, C3, and this is C4, and they have been connected across a 500 volt supply. So let's say this is 500 volts supply, and they have named the terminals as A, B, C, D. These are the 4 junctions. Okay. ठीक है बच्चा, C1, C2, C3, and if this is the plus side of the voltage, this is minus. So obviously this will be plus, this would be minus. So this is plus, minus, and this is connected. So these two will be plus, and the end one will always be minus. And then you should have by induction. So this is plus, plus, minus, minus, and plus, plus. Automatically it will tell you. You need not worry, right? How to do it? See, always do it in this manner. This is plus, this is minus. So this will get plus, minus, and out here this plate gets plus, this plate gets minus. Rest all by induction. If this fellow is plus, this fellow has to be minus, this fellow minus, this fellow has to be plus, right? Our first job is to find out equivalent capacitance. Equivalent capacitance. So when we are trying to find out equivalent capacitance, what are we assuming? We are assuming that there is one capacitor and there is the 500 volt supply. ठीक है ना? This is plus minus, plus plus, minus minus. This is the equivalent capacitance of C. So how is the network looking like? I think C1, C2, C3 are in series, right? These are in series, ringa ringa roses, and their equivalent is with C4 is in parallel, right? So in series, what happens? It's just opposite of resistance. So we say equivalent, equivalent capacitance for C1, C2, C3 in series. So we'll say 1 upon C1 is equal to, 1 upon, so what do we use? You have to use something like 1 upon CS, okay, is 1 by C1 plus 1 by C2 plus 1 by C3. So that's 1 by 10 plus 1 by 10 plus 1 by 10. But they are in microfarad. Okay. 1 by 10 plus 1 by 10 plus 1 by 10. So how much is it? 10 divided by 3. So the C series is equal to 10 divided by 3 microfarad. Is this, children, okay? All right. Now, so your diagram now becomes something like this. This is the C series. This is in parallel with C4. And then you are supplying how much? 500 volts. All right, plus minus. So these two will be plus and these two will be minus. Now CS and C4 are in parallel. CS and C4 are in parallel. So C will be equal to CS plus C4, which is 10 upon 3 plus 10. So that is 40 upon 3 microfarad. Did you understand, Arjun? Okay. That was the first part. So far, okay? Okay. Fine. Now we have to find out what is the charge on each capacitor. Now children, 1 minute, okay? So we found out that the equivalent capacitance is how much? 40 divided by 3 microfarad. Agreed? How much of voltage are you supplying? 500 volts. Can you not calculate what is the entire charge of the circuit? How much of charge is moving in the circuit? So how much charge should be moving in the circuit? The amount of charge that is moving in the circuit, you know, C is equal to, Q is equal to always CV. Q is equal to CV. So C means 40 divided by 3 into 10 to the power minus 6 multiplied by the voltage of 500. So 500 means 100 and 2 gone, 10 to the power minus 4. So this would be 4 5s are 20, 200 by 3 into 10 to the power minus 4. So we can write another 2 gone. So 2 by 3 into 10 to the power minus 2 coulomb. This is the net charge. The net charge. Charge and current are all same, children. Look. So that means on this branch and on this branch, right? The current is actually, it is going here and it is going here, and these two should be equal. And if these two are made equal, then here it is again divided into 3. The charge gets divided into 3. So between the two parallel wings, how much of charge can I expect? Okay, the charge on Q4 should be how much? This entire network is what, beta? This entire network was CS and this is C4. Agreed? And how much was the voltage? 500. You know the value of both CS and C4. Right? Can we now calculate what is the what do you call, and the net charge is how much? The net charge is 2 by 3 into 10 to the power minus 2. Can you calculate how much should be the charge here and charge here? Let's say for Q4 will be C4 into V. Agreed or not? C4 into V means how much was C4? 10 into 10 to the power minus 6 multiplied by 500. So how much are you getting? Just check. You're getting, so this is 1 2 3, right? 1 2 3, 5000 into 10 to the power minus 6. So it becomes 5 into 10 to the power minus 3. To make it minus 2, how much it should be? It should be 0.5 into 10 to the power minus 2 coulomb. Agreed? This 0.5 into 10 to the power minus 2 coulomb, if you subtract from here, you get what is the value of CS. And that when you divide by 3, you should be getting the value of, because all the capacitors are same. If you divide by 3, the charges, no, hang on. Why will you divide it by 3? You won't divide it by 3 because the same, it's current, is the same charge that is flowing out here. So 0.5 into 10 to the power minus 2 coulomb is the charge here. So if we subtract these two, 2 by 3 means how much? 0.6. 0.6 minus 0.5 is 0.1. So the charge that is flowing here, that is say QS, should be 0.1 into 10 to the power minus 2 coulomb. Have you understood? This is 0.6 minus 0.5. And that should be the same charge which is going all across. Because in series, charges don't get distributed. Yeah, they have said 5 into 10 to the power minus 3 and 1.7. And I said 0.1. So that's just same. Did you understand or not? Just apply like resistors. If you have your common sense, you should be able to solve it. You know the entire charge in the circuit. The charges flow, so they get two routes. In this route, they'd have no more merging. See, if you use little bit of common sense, you should be able to solve it. How much charges started to flow from here? The net amount of charge Q was how much? 2 by 3 into 10 to the power minus 2 coulomb. So many charges are going. They get one this track, one this track. On this track, how much charges went? 0.5 into 10 to the power minus 2 coulomb. So on this track, how much went? 2 by 3 minus 0.5 into 10 to the power minus 2 coulomb. Is there any more bifurcation? Is there any leakage chances? No, the same charge is flowing out here. In short, if you apply grade 10's concept, you basically said I current went from here, split up into I1 and I2. That's it. Okay? These type of questions you get. Calculate what is the charge, Just don't goof it up like resistance format. Okay, so you have time, we'll start current electricity then. That's our third chapter. So electrostatics comes to an end, charges being at rest comes to an end. From now on, a new fellow will be born whose name will be current. So we'll just make it